We're going to talk about the chapter 9, electrical properties. We have so far we have talked about optical properties. That is chapter 8. Okay, chapter 9 is electrical properties, and chapter 10 is the magnetic properties. Okay. Well, if you want to talk about the electrical properties of the solids, then naturally you have to talk about the conductivity. Conductivity of the material. Now, the conductivity of the material is the number of free carriers and then charges each free carrier can have, and then mobility. That is the general equation for the conductivity of any material. And N is the number of free carriers. And then mu is the mobility. So in this chapter, we're going to talk about the electric field effect and the temperature effect on the free number of free carriers and the mobility of the materials. So we are going to talk about the 9.1, the effect of electric field applied to the solid on the number of free carriers. And then we are going to talk about the electric field effect on the mobilities. That is 9.2. And 9.3 is electric mobility effect of a temperature on the mobility of the material. And finally, we are going to discuss about the effect of temperature on the number of free carriers. All right? Before we go into the details on this, let's just think about the conductivity definition. Conductivity is number of free carriers, of course, that is important, and the mobility is important. And as far as the mobility is concerned, velocity, okay, velocity is mobility times electric field. In other words, if you plot the velocity and electric field, then we're supposed to have a straight line in a certain limit. That is the critical electric field. Okay, and then the slope is corresponding to the mobility of the material. And the mobility is a material constant. For instance, silicon, the mobility of electron in silicon is 1,420 centimeters square per voltsec. That has determined, okay? And of course, the velocity of the electron is changing dependent on the electric field applied to the material. And after the critical electric field, it is no longer straight line, and then it's supposed to saturate. The velocity saturate. Okay? And it's because the inelastic scattering of electrons with a lattice wave between electron wave and lattice wave. So mainly we are going to talk about the mobility, velocity of electrons up to this critical electric field. And after that, it is not predictable. And it is not that much important. Now, the velocity is concerned, we're going to have two velocities. One is the drift velocity, and the other is thermal velocity. Drift velocity is the velocity that can be defined as something like this, all right? Let me make it consistent. That is a drift velocity, and this drift velocity is typically 10 to the 5 centimeter per sec. Somewhere around there, okay? And thermal velocity is the kT, the energy is the kinetic, it can be written as a kinetic energy like this, okay? The thermal vibration of electrons, and it can give us the velocity. And then in this case, the thermal velocity is typically 10 to the 7th centimeter per sec, okay? So that's a little bit different. And the mobility, we have deduced the mobility, the equation related to the mobility, and then intuitively what we have is that the mobility of any substance is inversely proportional to the weight of the material. The mass is inversely proportional, and then the charge it has, and then scattering relaxation time. Remember the velocity, if you plot the velocity of the electrons, or the time or distance, whatever, then it goes in elastic scattering range. It goes like this, so that the average velocity is somewhere in here. And then from here to here, we call that scattering relaxation time. And during that time, it's going to be accelerated so that the mobility of electron should be proportional to the time for the acceleration, and then inversely proportional to the weight, something like that. So we don't have to go for the details in the mathematics to deduce this equation, but the momentum is the force of the integration with respect to time, so that this is m star v, that is the momentum, and then that the force integration is going to be related to the scattering relaxation time, something like this, right? And then this v is q electric field mobility, right? That is the velocity. And then that is equal to the q electric field and scattering relaxation time. So you take out there's all values, and then you turned out to, oh, wait a minute. We don't have a q here, right? So the mobility now is going to be q tau as c. That is a simple derivation for the mobilities, right? From here to here as the mobility derivation. Now let's talk about the free carrier density effect of an electric field on the free carrier density. We are going to talk about the three phenomena as far as free carrier density dependence on the electric field. We are going to talk about three phenomena. And the first is impact ionization. Impact ionization. And secondly, field emission. And lastly, electrical injection. Okay. Impact ionization is the phenomenon related to the generation of free carriers by applying high electric field to the electrons on the conduction band. For example, the OJ electron is nothing but the generation of electrons by, if you apply the electric field, then the electrons are trapped in the trap site. It's going to be excited to the conduction band. And this electrons excited to inside the conduction band, when it dropped, then generate the energies. And this energy we're going to give rise to the OJ electrons. That's how the generation of, that's how we can generate the OJ electrons in a solid. Okay, this is one example. And impact ionization happens whenever in a silicon matrix, for example, if you apply the high electric field, then you can generate the electrons and holes with the high electric field. The valence electrons in the solid, okay, this electron is going to be freed by the high impaction of the high energy electrons due to the high electric field. That is the impact ionization. And the field emission, so that we can generate a lot of electrons, free carriers, by applying the high electric field to the solid. Okay, the field emission is done, it can be pictured something like this. If you have electrons trapped in the conduction band and the valence band, when electric field is not applied, is not applied, then the band structure is going to look like this. Okay? But if you apply the electric field, then now the band is going to be changed with some slope, okay? Valence band, and then the defect levels or impurity levels is going to change accordingly, okay? You are going to have a slope when the electric field is applied to this material. If you apply high electric field, then this band is going to be tilted more angle, and then the movement of electrons to the parallel direction is not it does not cost any energies, because this y-axis is the energy. This is the physical distance. So if you move laterally, then you don't need any energies for the electrons to move, right? So you can go into the conduction band without any cost of energies if you apply the electric field, right? And that is going to be called the tunneling phenomenon. And then you can create a lot of electrons, free carriers, on the conduction band in this way. That is the the field emission. Now, field electrical injection is just a injection of electrons, localized injection of the electron to the solids. Now, if you have a solid like this, and then with a probe or whatever, you apply high electric field, then electrons is going to be injected locally on the solid. Now, if it is a metal, then the lifetime of this injected electron is very short, so that it will be dispersed in a less than a second. But if it is an insulator, then the lifetime of this electrons is going to be, we call that the relaxation time, right? Relaxation. Relaxation time is very big. It can reach to 1,000 seconds in an insulator, so that it can live 1,000 seconds if you inject the electrons on the insulator by high electric field. If it is a metal, then the relaxation time is 10 to minus 5 or 10 to minus 6 a second, something like that. So it immediately, you cannot localize the charges and the metals. But if it is a semiconductor or insulator, then this way you can create a new electrons. Okay, the next topic is the electric field effect on the mobilities. Electric field effect on the mobilities. Okay. the mobility of any materials, up to critical electric field, the mobility is the material constant. But after this critical electric field, then the mobility is going to decrease, okay, by saturation. And that is due to the inelastic scattering of the materials. Now, if you increase the electric field, then the velocity is increased, but the relaxation time for the scattering is going to decrease, so that the mobility is going to decrease. Okay? And usually the critical electric field is the velocity of the sound, which is 10 to the 5 centimeter per sec. That is usually the critical electric field can be determined something like this. This is the material constant. The constant values were here, mu naught, okay? And then the critical electric field happens typically on the velocity of the sound. So I just mentioned that when as electric field increase, okay, and then velocity of electron is going to increase, but scattering relaxation is going to decrease, okay? So that is a controversial thing, which makes the mobility goes down. So if you increase the electric field, then eventually you can decrease the mobility of the free carriers, okay? So that's electric field effect on the mobilities in general. Now, more important thing is with the mobility change with respect to the temperature. That is more important than the mobility change with respect to the electric field. That is 9.3, mobility change with respect to the temperature. Because the temperature is the most common thing that we use as the variable of the thing, right? So in this analysis, what we are going to do is we're going to use the mobility equation that we have discussed. Okay. Then we mainly concern about this relaxation, scattering time of the material, scattering time dependence with respect to the temperature. Now, the one thing we should think is the mean free path. Okay, that is the mean free path means the distance of free carriers moved, the distance of free carrier can move before the scattering, between the scattering events, whatever, okay? And then this mean free path should be proportional to the 1 over T, because if you increase the temperature, then then more vibration happens so that the mean free path is going to decrease. So it should be inversely proportional. And then scattering time is going to be related to the 1 over velocity, the distance, and then it should be related to the mean free path, something like that. Okay? So, as far as the electric temperature effect or whatever, the scattering relaxation time is concerned, then this scattering time is going to be proportional to 1 over temperature and the velocity of the materials, something like this. And we distinguish two things here. One is the scattering by acoustic wave scattering, and the other is the charged impurity scattering. We want to analyze this scattering time in these two cases, okay? If you don't have any charged impurities in your materials, then this is not important. But if you have charged impurities in your materials, then both acoustic wave scattering and charged impurity scattering, both phenomena has to be considered, okay? So let's think about this acoustic wave scattering first. We have two cases. One is a semiconductor, where we have a limited number of free carriers, and then we're going to have a case for the metal. Okay? In a semiconductor case, the KT, the thermal energy, is related to the mv square, okay? The kinetic energy. And so the velocity of free carriers is going to be proportional to the square root of temperature. And scattering relaxation time, which is proportional to the temperature and the velocity, should be proportional to the T to the minus 3/2. So the lattice acoustic wave mobilities, okay, which is going to be proportional to the scattering relaxation time, and that is going to be T to the minus 3/2. That should be proportional to the T minus 3/2 power. Okay? In a metal case, the velocity of free carriers, we should talk about the free carriers on the Fermi energies. Most of the free carriers free carriers are on the having ferromagnets in a metal, because almost all of the free carriers are concentrated on the fermi energy levels. And then we know this fermi energy is not related to the temperature. Okay, so in a metal case, the scattering relaxation time is just proportional to the L or fermi energy velocity, and then that is going to be 1 over T. Okay, so in a semiconductor case, in acoustic wave scattering, the mobility should be related to T to the minus 3/2 power, but in a metal case, the mobility should be related to the T minus 1. Okay? But if you have a scattering by the charged imperfections, now what we are going to think is that if you have a charged impurities like this, and then if you have electrons passing by this charged impurities, then it is going to, otherwise it goes straight, something like this, it's going to change the directions, okay? And we call this the scattering, okay? And then the cross section that this charge can affect on the electron path, this is the effective scattering areas, scattering centers, which can affect, which can relate it to the scattering events of the electrons. So we want to calculate the radius r so that we have a cross section for the charged impurity scattering, and then we want to relate that with the temperature, how this cross section is going to be changed with the temperature. All right? So the critical radius here, the R sub C, it can be get from the d q square over dielectric constant is kT. That is the coulombic energies. And then R sub C is z q square over dielectric constant kT. And we know that is related. And then scattering cross section is equal to pi r sub c square, and then this is going to be related to the t minus 2, okay, with this equation. And the scattering rate all right, scattering rate is equal to 1 over tau scattering relaxation time, and that is going to be density of impurities, charged impurities, and this cross section of impurities scattering, and the velocity, thermal velocity of the electrons, free carriers. So the scattering rate is going to proportional t to the minus 2 for the cross section, and thermal energy term, which is proportional to the t to the square root of t, so that mobility of a charged impurity scattering case should be proportional to the scattering relaxation time, and then that is going to be related to the t 3/2. Okay, and then you can distinguish that in the acoustic wave scattering case, t to the minus 3/2, and then charged impurity case, t to the positive 3/2. So, if you have a material where one of the more than one scattering event is related, then you should add up all those mobilities due to different scattering events, and then summation is going to be done total mobility is equal to 1 over mobility the lattice acoustic wave scattering, and then if it has the charged impurity, and then whatever, you should add it to something like that. And then if these two are important, then this should be AT minus 3/2 plus BT positive 3/2. It should go something like this, okay? That is 1 over mu total. So if you have a plot for the mobility with respect to the temperature, then you have one straight line for the acoustic lattice wave, T3 minus the 3/2, and that is the acoustic lattice wave scattering. And then the other straight line where the charged impurity scattering, charged impurity scattering. And then that is T to the 3/2. So if it is added, finally what you're going to have in your material, you're going to have a temperature dependence of the mobility, something like this. And then the important feature of this is that you are going to have the temperature which shows the maximum mobility of the material, maximum mobility of the free carriers. So this is the amazing thing, actually. With this analysis, in any material, you're going to have a temperature which shows the maximum mobilities. Maximum mobilities of free carriers. So this temperature, you have to notice that there is a temperature which makes the free carriers most mobile, okay? On Wednesday, we're going to talk about the final topic, the free carriers dependence on the temperature. This is the most important features among these 4 categories that we have discussed. And then we're going to devote 2 or 3 lectures just for this, starting on Wednesday. Okay?